All right, how's everybody this evening? I think we're ready to get going. Where do you want to start? Sure, there you go.
Hello. Good afternoon, Professor Cascarano. I had a question concerning one of your PV diagram videos. I believe it was chapter 18, part 11. When we were finding the work, there was a part where in the equation where work is equal to nRT, and then there was something on 1n V final over V initial. I was wondering if you could kind of explain that. I don't really know where that came from, so I was wondering if you could please explain that.
Yes, I can. So that's for, well, anytime you have a curve on a PV diagram, the work is equal to the area under the curve. It doesn't matter what the shape is, right? If we wanted to know the work done in moving from point A to point B along this path, it's the area under that curve. We happen to use some that are easy, right? If P is constant, then finding the work under there is very easy, right? It's just P times the change in volume, right? If it's a straight line, then you can break that up, right? We know how to find the area under a triangle, and we can find this area easy enough, and we can just add those together to get the total area under that curve, right? So those are pretty straightforward. The two other, and then of course there's one more that's easy, right? Constant volume. That's an easy one. Okay, so the two others that we use a lot of are the adiabatic process and the isothermal process. The adiabatic process is not easy, but the isothermal process is not bad. So an isotherm looks something like this. If you're told that that's an isotherm, you know, in other words, anywhere on that curve, the temperature is the same, right? Isothermal process. That means temperature is a constant. So when you integrate, you get an integral of 1 over the volume. You integrate to get the area under the curve, right? If this was a calculus-based physics class, we would want to try to find the area under that curve. And so what you're doing is you've got PV equals nRT. So P is nRT over V. And what you're doing is you're integrating to find the area under here. It's the integral of this something like that. Yeah, something like that. So anyway, N, R, and T are all constant. It comes out. I don't know how much calculus you've had yet. And the integral of 1 over V is the natural log of V. And you're going from V1 to V2, so you get the area is nRT times the natural log of V2 over V1. So that's where it comes from. But since we don't do calculus here, the book just gives it to us. And it would be, where would they give it to us? Probably in chapter 17. Oh, no, it's in chapter 18 on page 617. So it's the work is equal to, nRT times the natural log of V final over V initial. So as far as we're concerned for this class, we would just be given this formula. I think it's on the formula sheet. And you're finding the work done. And it should work out properly. If V final is greater than V initial, the work done should be positive. And the natural log of a number greater than 1 is positive. If V final is less than V initial, then we have the natural log of a number smaller than 1, which is negative. So the work would be less than 0. So it works out nicely. It gives you the right sign if you plug in the volumes correctly. Okay, did I answer your question? Yes. Only for constant temperature. Right, these other processes, right, if you're at constant P, there's our equation for the work done. It's the area under the curve. If the V diagram curve is linear, then you just use your geometry, right? You know how to find the area under a rectangle or a triangle, right? So you just find the area, right? A constant volume process has no work done. An isothermal process, here's our formula, and those are the ones that you need. For a adiabatic process, what you usually do to find the work done So here's your PV. Adiabatic looks something maybe like that. What you usually do is you find the temperature at A, you find the temperature at B, and once you know the temperatures, you can find the energies, right? And once you know the energies, you can find delta U. So now we know delta U for this process. And what is Q for an adiabatic process? 0. And we know our first law of thermodynamics. So if we know delta U and we know Q, then we can solve for W. That's usually the way we do it for an adiabatic process. There's no simple formula. Okay, entropy. Let's see. Okay, so oftentimes these problems will have something like a phase change or our formula is this. The change in entropy is Q over T. So we're looking at something typically that's happening at constant temperature. And so one thing that can happen at constant temperature is a phase change. So a common example is an ice cube melting. So if they tell us that an ice cube is something, what do we want, 0.1 kilograms, and we want to melt it, what we say is that the change in entropy is Q over T. So the first thing we have to figure out is how much heat we have to put in to melt the ice. and that's going to be the mass times the latent heat of fusion. And what is the latent heat of fusion? Yeah. 33.5 times 10 to the 4. So that gives us some value, whatever that is. That's 33.5 times 10 to the 3rd. And we know that this is happening at 0 degrees C, but of course, anytime you see a temperature by itself, we have to use Kelvin. So that's 273 Kelvin. So our change in entropy is 33.5 times 10 cubed joules over 273 Kelvin, and whatever that is. And the answer is joules per Kelvin. We just leave it as joules per Kelvin. So typically with these processes, and it increases, right, because Q is positive. If we are putting heat into the substance, Q is positive. So in this case, the entropy increases. And if we're pulling heat out, Q is negative, then the entropy would decrease. Another thing that you could do is the entropy change like for instance for a refrigerator or an air conditioner. So you can show that the change in entropy of one of the things is going down, the change in entropy of the other one is going up, but the one that's going up is always more than the one that's going down. So that the law here, second law of thermodynamics, says that the entropy is always increasing. The entropy of the universe is always increasing. So if we are looking at, you can look at individual steps. Some might decrease, some might increase, but overall the entropy is going to increase. So an example is letting heat flow from a hot place to a cold place. Your book, this is in your book. So this is just heat flowing . So they picked some number. 1,050 joules of heat flows from a hot reservoir, and they let their hot reservoir be 576 Kelvin, and their cold 305. So heat's flowing from the hot place to the cold place, and we want to say, well, the change in entropy of the hot place is going to be Q over T, and Q is negative because it's coming out, and T is 576. So whatever that turns out, let's see, they did it 1.82. And the change in entropy of the cold place is Q cold over T cold. Q cold is positive 1,050. But you see, we're dividing by a smaller number now. So we're going to get a larger change, positive 3.44. So when we add these two together, we say, what happens to the universe? Oops. we got the hot place was negative 1.82, positive 3.44. We get a positive number, 1.62 joules per Kelvin. So the change in entropy of the universe was positive. Sometimes they'll give you problems where energy is coming from the sun to the earth, something like that. So the energy is flowing from one place to another. The thing that's getting the energy, its entropy increases. The thing that loses its energy, its entropy decreases. But because the temperature is hotter when the energy comes out, and the temperature is in the denominator here, you always get a smaller negative change in entropy than you get positive. So the net change in entropy is always positive. It's an arrow of time. It tells us, it's a way of quantifying. Physicists want to know, how can we quantify, what direction something's going to go in time? If you take a movie of something and you play it backwards, do we know whether it's going forward or backwards? Right. So if there's a I don't know, a glass of water sitting on a table, and we're watching a movie of it, forwards, backwards, it's just a glass of water sitting on the table. If there's an ice cube sitting on the table and it's melting, and we watch a movie of it and we play it backwards, we know it's going backwards, right? It's obvious to us that a pool of water on the table is not going to form into a block of ice. We know that that's not going to happen. So physicists want to come up with an equation that tells us which direction something's going to go. And so that's what entropy is all about. It tells us which direction something's going to happen in nature, and quantifies that. And we can look at the numbers and know what's going to happen based on the change in entropy. The change in entropy always has to be positive. The entropy of the universe always has to increase in natural processes. Or if we make it decrease, like a refrigerator might make it decrease on the inside of the refrigerator, on the outside it's going to increase by more than it decreased on the inside of the refrigerator. So the net change to the universe is positive. Good? Okay, so a couple of examples there. The first one here, very common problem, and the second one is sort of another common way of looking at it. But those types of problems for entropy change. For efficiency, no, you might not be given it. You might be asked to calculate the efficiency. So for an engine, we usually use the term efficiency for an engine, and COP, a coefficient of performance, for a refrigerator or a air conditioner or a heat pump. But in any case, they're really the same thing. It tells us how efficient it is at doing what it's supposed to do. And it's always, whether it's the efficiency or the coefficient of performance, doesn't matter. It's always the desired the desired process divided by what goes in. Right, what you have to put in to make that happen. Same for this. So for an engine is doing work, right? We put energy into our engine, we get work out, and we have some exhaust, right? Because of friction, or we lose a little bit of heat to the environment. Some energy is lost in this process. So the efficiency of this is the desired output. Well, what is that? If this is an engine, it should be doing work, right? That's the desired output, is the work. And what are we putting in? Q hot. So that's the efficiency of an engine. If we're looking at like a refrigerator, then what's the refrigerator doing? A refrigerator is actually removing heat from the cold place and dumping it to the hot place. And how are we doing that? That would not normally happen, right? Well, we're putting work in. We're doing work to make that happen. So the coefficient of performance is the desired output. The refrigerator is supposed to make the inside. This is the inside of your refrigerator, right? And this is your room, your kitchen. So a refrigerator is supposed to make the inside of your refrigerator colder. So the desired output is removing heat. The desired output is Q cold, right? We're trying to remove heat from the inside. And what do we have to put in? We have to put in W. Now, an air conditioner looks very similar to a refrigerator. What does an air conditioner do? It takes heat out of a cold place. This is your room, right? And it dumps it outside on a hot day. And you have to put work in. Just like a refrigerator, right? The model here, the picture I just drew, the diagram, looks identical. QC comes out of the cold place. Q hot goes into the hot place. We have to put work in. But what's the desired, let me see. Do I have that right? No, that's really the same. What am I thinking of? That's the same. No, I'm thinking of a heat pump. Let me do this. So this is the same. This is the same coefficient of performance. Right, because the desired output is removing the heat from your room, and you have to put W in to do that. A heat pump works the opposite way. We don't use heat pumps in California typically. So a heat pump is a way to heat the house. It removes, this is the outside, right? So it's winter time. That's outside your house. And you bring heat into your house. Oops, that's a W, sorry. Right. So again, this diagram looks just like the other two. An air conditioner and a refrigerator are basically doing the same thing. They're removing heat. The goal is to remove heat from the cold place. The goal in a heat pump is not to remove heat from the cold place. The goal is to add heat to the hot place, right? You're trying to warm up your house. The desired effect is dumping heat into your house. That's what you want. So it's Q hot is the desired thing. You're trying to heat the inside of your house. You're trying to have Q hot dump into your house, and you have to put W in to do it. Okay, so not sure if I answered your question, but I just kind of wanted to run down efficiencies and coefficients of performance. They're really the same thing. It's a way of telling us, you know, how much are you getting out for what you're putting in. It's a way to judge the efficiency of the process. Okay, good. Chapter 18, 51. Okay, so for the first part, we're just in need of the so the car, they tell us Carnot. When it says Carnot engine, that means this is the maximum efficiency process we can have. And we know this equation So they gave us the efficiency. We're trying to find T cold. They gave us T hot. So we can solve for T cold in terms of in Kelvin. So what is it? 0.7 times 545. Now we want to increase the efficiency, right? So 40%. And so what do we have to do? We have to make the efficiency better, usually you need a bigger swing in temperatures between T hot and T cold. The closer T hot and T cold are to each other, the harder it is for this engine to do work, right? So the bigger the temperature difference, the more efficient. So you have to lower T cold to increase the temperature difference. Or if you just put in, you can plug the numbers in. They gave us 3 of the numbers. You can solve and you'll get a lower T cold now. Oh, and then as part C, it says solve for T cold. So the trick was, up here I showed you, where was it? Here. Efficiency, work over Q hot. We can rewrite that. We know the work. We know from conservation of energy what goes into the engine must come out, right? Q hot is going in, and coming out is W plus Q cold. So we can rewrite this as Q hot minus Q cold over Q hot. And we can rewrite that as 1 minus Q cold over Q hot. Right? Those are all equivalent. And then when we get to Carnot engine, when you're dealing with those maximum efficiency Carnot cycles, reversible processes, we can make this change that the maximum efficiency, or the efficiency of a Carnot engine, Carnot cycles, is just 1 minus T cold over T hot. But this is only for maximum, this is only for a Carnot engine. Okay, good. Excellent. What else we got? I'm looking to see if I can find one in the book, because it's hard to make up numbers, because then you get into trouble. They don't make sense in the end. No, that's okay. Okay. So we're go through some sites. So maybe we'll do something similar to okay, so we'd have to be given some information to sort of get started on this problem. Let's say, so usually I like to make a little table of states. So we've got A, B, and C. And what do we care about? P, V, T. And once we know T, we can find U, the energy. So maybe we're given the pressure and volume maybe those are given. So if we know two of these, we can solve for the third one, assuming we know N, using PV equals nRT. So if we know P and V, we know N and R, we can solve for T. And if we know T, then we can find U. So we've got A filled in. And maybe they only gave us this other information. And that's it. We know the volume at C is equal to the volume at A. That's a given. So we don't have enough information to solve for TB or TC. So it seems like we're stuck. But we know something about this process that connects A and B. That's an adiabatic. That's an adiabatic process. And something is true for adiabatic processes. P V to the gamma is a constant. So that's what we know. That means that PA, VA to the gamma has to equal PB, VB to the gamma. And if this is a monatomic ideal gas, gamma is equal to 5/3. So we've got P at A, V at A to the 5/3 power. is equal to P at B, V at B to the 5/3 power. And we know PA and VA, and we know VB. So we can solve for the pressure at point B. Okay, so this is one of the reasons we use the adiabatic process. It has this special property. It's one that helps us sort of figure out what's going on. And we also use it because it means Q equals 0, right, in an adiabatic process. And that's something that we can do. We can either do a process very quickly, so Q doesn't have a chance, the heat doesn't have a chance to leave. Let's say we have a gas in a cylinder and we compress it very quickly. The heat builds up in the gas, but if we do it quickly, the heat can't leave the container yet. So that's an adiabatic process. Also, we can make a nice insulated container so that as we heat the gas, the heat can't escape. It's a nice insulated, well-insulated container, and so the heat stays in. So we can create this. It's a process that we use. So we can solve and get the pressure at B. And once we have the pressure at B, oops, what did I do here? There we go. Once we have the pressure at B, we know that that's the same as the pressure at C. Those are the same pressure, right? So now we know two of the three things for B. We can use PV equals nRT to solve for the temperature. And once we have the temperatures, we can solve for the internal energies. And then once we have this table filled in, we can make the table for the process steps. So that's from A to B, from B to C, and from C back to A, right? Those are our three process steps. And what do we care about? Delta U, Q, and W. So the delta U's are easy because we know UA, UB, and UC. So this one is just final minus initial, UB minus UA. This is UC minus UB. It's important you get them right because these might be positive or negative. We don't know which they are. You got to get the numbers right. And this is UA minus UC. So could be positive, could be negative. Q's, we only know one of them, and that's this one. Nope, that's not right. It's the adiabatic process from A to B. We know Q is 0 for that process. And we don't know B to C or C to A yet, but what we do know is the work done for those two processes. Let's start with the easy one, C to A. From C to A, the volume does not change, so the work done is 0. From B to C, this is just a constant pressure process, so we can find the area of that rectangle, and that's the work done. And it's negative because V is decreasing. Actually, it's delta V would be negative, I should say. Okay, so we can find that. Now we know 2 in any column here. In this column, I've got 2 out of the 3 things. In this column, I've got 2 out of the 3 things. In this column, I've got 2 out of the 3 things. So I can use our first law to solve for the missing one. So in this case, it's going to be equal to negative delta U. And in this case, it's going to be equal to delta U. And in this case, it's delta U plus the work done. And remember, the work done is negative. Okay, so it's the same process that we used in that video to solve. We had a similar one. The video, that wasn't an adiabat, right? It was an isotherm, but otherwise it was identical, if I remember correctly. So it's the same process, only in this case, we thought we were stuck, right? We were missing 2 out of the 3 things. We thought, wow, how do we do that? We're missing a piece of the puzzle, right? But because it was an adiabatic process, these were linked. These 4 things are linked together. And so we knew 3 of them, and we could solve for the 4th one. Okay, good. I'm pretty sure I did a solution video where they have all 4 process steps. I don't remember exactly. Let me see if I can find it here real quick. Yeah, I think it's Thermo 53. There are 4 process steps, one that's isobaric, one that's adiabatic, one that's isothermal, and one that's isochoric. So it's got all 4 examples in there. Right? One, I don't know what it looks like exactly, but it's got all 4 process steps in there. So take a look at that one, the solution video, if you haven't looked at that one yet. I might even have one on, let's see. Yeah, I've also got one refrigerator and one entropy problem there, so you can take a look at those also. Okay, that'll get you going for tomorrow, or for a little more studying tonight. All right, sounds good. Good luck tomorrow.